Welcome everybody to this webinar of Xsens and AnyBody. My name is Felix and I will be your host today on behalf of Xsens. I would like to start by going over the agenda. As you can see, my colleague Marcus Skekbrand will kick off. He will tell a little bit about Xsens as a company, also going into depth about the technology. So how can we get kinematic data out of the IMUs that we are using? He will also tell a bit about the integration specifically with AnyBody. Then Pavel from AnyBody will take over. He will tell about AnyBody as a company, but also about the software, the AnyBody modeling software, obviously. Then we have two external speakers. We have Sebastian Schals for the National Research Center for Working Environment based in Denmark. He used the combination Xsens AnyBody to estimate joint forces, and he focused on manual material handling specifically. So it's really about ergonomical applications, where on the other hand, we have Jason Conrad, the CEO and founder of Principia Technology, who also used the combination Xsens AnyBody, but he used it as a tool to look at the activity from elderly people, mainly focused at the knee. So he was looking at, for example, joint forces in the knee, as well as knee adduction and the effect on the daily activity. At the end, we will go over a live Q&A session. So if you have any questions, feel free to post them in the GoToWebinar question box. I will make sure to answer the questions on behalf of you, the audience, to the right presenter. If we run out of time, we will make sure that the questions get delivered to the right presenter, so you get in contact after the webinar. If you have any questions popping up once the webinar is already done, you can always send an email to info@xsens.com. We will also make sure that the question get delivered to the right person. The same goes for any other questions, or if you just need information or be in contact with one of the presenters. This session will be recorded, so you will get a link afterwards where you can find the recording, watch it again, and maybe share it with people who you think this might be interesting too. We will also post the recording of the webinar on our website. So also if you want to see other webinars that we did in the past, feel free to go to Xsens and to take a look at the webinars that we made. So without further ado, I would like to give the word to my colleague, Marcus Skekbrand, who will talk a bit about Xsens.
As Felix said, my name is Marcus Skekbrand. And the topic of today's webinar is the integration between Xsens and AnyBody. But first, I would like to tell you something about Xsens and our technology. So Xsens is the leading innovator in 3D motion tracking technology, and we have been around since 2000. Today, we have 5 regional offices across 3 different continents, and over 120 employees work at Xsens worldwide. As you can see, we also have a big worldwide network of distributors and resellers. But what is it that we actually do at Xsens, and what is it that characterizes Xsens in our technology? Well, the core of Xsens technology is sensor fusion. We are specialists when it comes to combining data from different sensing elements to provide highly reliable motion tracking data. Sensor fusion is what enables us to offer a whole host of solutions, everything from individual sensors to full body motion tracking systems, while also giving us the possibility to offer our customers with highly unique features, such as full immunity to magnetic interferences. Our offerings at Xsens can be divided into 3 key business lines. The first one is inertial sensor modules. So this is where our sensors are used for industrial applications such as robotics, navigation, autonomous vehicles, offering accurate positioning and orientation. The second one is our wearable sensors platform, offering developers and innovators an easy-to-use and affordable platform to develop their own application in human kinematics. The last one is, of course, 3D body motion. this is where we offer full-body inertial motion capture systems that offer lab quality data in field conditions, in 3D kinematics for research, but also for 3D character animation purposes. Now, I would like to show you a video that was made by my colleague at Xsens, Maria Joao Cabral, showing you how you can export a file from on our ambient analyze software to a .bvh format, and then import it into the AnyBody platform. I hope that you enjoy the remainder of this webinar, and see you next time.
Hello, I am Maria. In this tutorial video, I will explain how to import Xsens data files in AnyBody. Open your recording in MVN software. In my case, the recording is simply a walking trial. First, we need to export our file in BVH format. To do so, go to File, Export and select BVH. Click in Show Options and guarantee that the box Overwrite First Frame with a T-pose is not checked. Then, click Export. Once exported, you can copy the file into the AnyBody directory. If you use the default options while installing AnyBody, this folder will be saved in your Documents folder. Paste the recording in Application, Mockup Examples, BVH Xsens and BVH files. To easily recognize the files in AnyBody, you should rename your file with the shown format, representing the subject number and the trial number. For multiple files of the same subject, change the trial number, and for multiple files of different subjects, change the subject number. Go now back to the folder BVH Xsens and go to the subject folder. Here, you find one folder for each subject. The easiest is to copy one of the folders and paste it again. Then, change the number of the subject to the same subject number of your file. When opening this subject folder, there is a folder for each trial recorded for that subject. You need to change the name of the folder to the exact name of the recorded file. Then, open the main script inside this folder. This script includes all the functions to run the model, and it also includes the scripts that you need to change according to each trial. The lab-specific data contains the information about the format of the file. Guarantee that the specifications are set to BVH files. In the subject-specific data script, the characteristics of the subject are defined. You should change these characteristics to fit the subject in your recordings. Finally, the trial-specific data script defines the settings of the recording. In this line of the code, it is specified that the trial name is equal to the current folder name. By changing the first and the last frame, you can select which part of the recording you want to analyze. After adjusting these parameters to your own recording, you can press the Load button to load your model. You can see that the motion data has been loaded, but not yet applied to the AnyBody model. To do so, you need to run the analysis. This processing involves multiple steps. The first one is a marker tracking, in which the virtual markers from the Xsens BVH model are mapped to the markers of the AnyBody model. An optimization algorithm is run to match both models. Afterwards, inverse dynamics is computed. The forces and the moments are calculated. An important feature that AnyBody developed is the possibility of also computing ground reaction forces by using kinematic data. You can visualize a representation of these ground reaction forces on the animation on the right side. Once the data is processed, it is possible to plot the different variables in a graph, and they can also be saved in a text file. To know more in-depth information about computation of ground reaction forces with Xsens and AnyBody, I would like to invite you to watch the webinar we did together. In our base platform, You can find an article with a video and a question and answer session during that webinar. For now, I hope you enjoyed this video. Thank you for watching.
Okay, thank you, Felix. Yeah, I will briefly introduce AnyBody technology. It's a company that produces AnyBody modeling system, a system for biomechanical analysis, also called musculoskeletal modeling. And today I'm going to talk about our interface to Xsens and exactly how to import BVH files. Basically, AnyBody modeling system is a system that is used in the fields of biomechanics, and these fields are quite broad, so you can use it in sports, in medical device and rehabilitation fields. You can also use it in the fundamental research and general biomechanics, in automotive, aerospace industries, in designing exoskeletons and assessing human-robot interaction, and of course in the fields of ergonomics and consumer product design. How does it work? The AnyBody modeling system is based on the human model, which is already created. So when you start working with the AnyBody modeling system, you just load a human model where you impose motion and external forces onto the human. You may want to add elements of environment, whether these are exoskeleton assistive devices or medical devices, and that creates a model. And once the model is assembled, we perform inverse dynamics analysis, which means that we go from motion to internal forces. And when we run the simulation, we get a vast amount of biomechanical data as an output. So we can look at the internal body loads, such as muscle forces, muscle activations, joint reaction forces. We could also measure all kinds of biomechanical parameters, such as energy expenditure, and so on and so on and so on. Once we are happy with our results, we can also send the data further to structural analysis, and everything can be designed, can be wrapped into an optimization loop where we optimize the design of our product. But the big question is, of course, how to define the data, because this is something that is very important for the analysis. And of course, if we have a very simple motion, then we can define it analytically. But when it comes to sophisticated motions, very heterogeneous movements, then of course you need very easy way to track the motion, 3D motion, and bring it into the system. And of course, this is where Xsens comes in. So they allow very flexible way to measure the motion, to record the motion. And in order to utilize these recordings, AnyBody created a dedicated processing model for BVH files. And this model comes as a part of the installation. So once you get AnyBody, it will be ready for you. So as you will later see in the video, you will basically copy BVH files into the folder that AnyBody can pick up. And once this is done, the model is practically set up. So what happens inside of this model is that the Xsens avatar will be converted to a stick figure, and AnyBody will use the stick figure to find the correspondence between the motion and how the human is supposed to look like. So we will scale the model, we will make sure that all the sizes of the human are respected, and we will also convert Xsens avatar motion to human motion, which means that we will optimize the motion to respect physiological constraints and also compute all the small joint angles, let's say clavicle elevation angle, and so on and so on and so on. Some features that are not present on the stick figure. And what we can do next is that we can add interaction forces, prediction of the interaction forces. For example, the flexibility of Xsens Suite is that you can measure your motion anywhere, and of course, without having force plates, it's quite difficult to measure external forces, but AnyBody has a flexibility of actually computing interaction forces. And these interaction forces can be, just a second. Basically, these interaction forces can be ground reaction forces, where we predict how much the ground presses on the human foot, or these are forces, for example, between the back of the this leg press machine, or the forces on the human feet. And then, for example, the forces when we press against a wall, or forces, for example, that are present between a device and the human body part. And these predictions, they were, of course, validated, and we looked at how the ground reaction forces actually predicted, and we have a really good correspondence between measured forces and predicted forces. And this was previously also presented in a joint webinar between AnyBody and Xsens. Yes, and once the model is set up, of course, you can apply it in different fields, as I already mentioned. And of course, ergonomics is a very interesting field to look at. And having motion recorded from Xsens allows us to do many different things. We can perform a very detailed ergonomic assessment of a workplace, where we can look at the ergonomic standards or conventional ways to assess ergonomic place, but at the same time we could also add an exoskeleton and see if this helps to solve issues. For example, on the screen you can see that ruler ergonomic assessment method suggests that this is a very bad situation, but we actually add an exoskeleton and we look at the compressive forces in the back, and you can see that they are actually not reaching red, and they are mainly green when the person operates with an exoskeleton. And this is what can be done in AnyBody, and you will hear a little bit more from Sebastian a little later on. So just to summarize, there are many advantages of having both products, so Xsens and AnyBody. And this is where we can really advance our biomechanics to the next level, so we can easily import and process data through a framework that was tested and set up to be almost automated. Of course, there are always some small things that may need to be adjusted. We can record human kinematics, and we can get down to very small physiological angles. We can output it in International Society of Biomechanics conventions if needed. We can predict interaction forces with the environment through simulation. And of course, we can look at the vast amount of biomechanical data as output. And this, of course, can be also automated and set up in a reproducible manner. So we can batch process all the simulations and get a reproducible outcome. And I think on that I would like to conclude, and I will pass the next word to Sebastian.
Yeah, thanks, Pavel. Indeed, Sebastian is next. So the first external speaker going in depth about ergonomical assessment with the combination of Xsens and AnyBody. Again, apologies for the sound earlier on with Xsens. We had the video without the sound, but we will make sure that the video is included with the sound in the recorded version. So you will get a link afterwards and can still watch the video. So Sebastian, feel free to take over, and if you have any questions, I see the first ones coming up. So feel free to ask the questions in the question box in the GoToWebinar tool, so we can cover them in the end.
Okay, I hope everybody can see my screen. If not, please let me know. So yes, welcome everybody, and thank you for tuning in. Today I'm going to talk a little bit about my PhD project, which involved musculoskeletal modeling of manual material handling in the supermarket sector. And it's particularly two things. If I can just, yep. It's particularly two papers from my thesis I would like to talk about, which involved a risk assessment study doing a lot of manual material handling tasks in the supermarket sector. And there's two publications related to this in applied ergonomics, which I hope you can check out if you're interested. And as well, we also published all the data in a supplementary database at sonodo.org. So check that out if you are interested in further information. So a brief introduction to why we chose the supermarket sector to perform this analysis. It's because we know that the supermarket sector has a high prevalence of manual material handling. And we also know that they have a high prevalence of musculoskeletal disorders. And this is particularly to the lower back, to the shoulders, the wrist, the feet, and the knees. But it's also kind of an overlooked industry in many ways from a scientific perspective, because the physical efforts doing stocking work, as it's called, are actually largely unknown. Like very few studies has actually gone in using direct measurements or biomechanical models to look at the physical efforts required to do the stocking work. So if you do this from a biomechanical approach, the traditional way has usually been to find some load estimate, either in the joints or in the muscles, and use this to compare to human strength capabilities or some injury tolerance limits. And one of the more famous examples would be the NIOS lifting equation, which also incorporates this an injury hypothesis, you could say, about the compression forces in the spine. So some of the limitations of these traditional methods, for example, if you take NIOS as an example, is it is quite limited in what kind of lifts it is able to assess or evaluate. Meaning, for example, that both feet has to be in the ground, the lift has to be in the sagittal plane, and it's not so suitable, for example, in highly asymmetric lifts. And furthermore, the biomechanical models used, for example, to develop this lifting equation are typically static, meaning that they considerably underestimate the loads compared with dynamic models. And at the same time, you have these two main limitations, that loads are only known for kind of idealized lifting situations that that you might not see in the field, or many lifts in the field doesn't fit into this this category or this definition. And of course, you don't get the actual loads because you don't have a true dynamic model to estimate them. So of course, we thought that musculoskeletal models might be the tool to overcome these challenges. And two reasons why musculoskeletal models or other complex dynamic models haven't been used, or if, of course, as Paul mentioned also, that they need they need external forces as input data and quite detailed kinematic data. But of course, these two recent developments, one being the availability of methods to predict the ground reaction forces, another one being the availability of inertial motion capture systems like the one from Xsens Technologies, means that we can actually get these input data from any environment or from in the field. So of course we were very interested to try this out and see how feasible it is to use and what we could actually get out of using this methodology. So we wanted to perform a risk assessment of manual material handling in the supermarket sector based on working postures, muscular efforts, and biomechanical loads. So how we did that, we recruited 17 full-time workers from 2 supermarkets and used this setup as you see here in the right-hand side on the pictures. We followed them around with this little table with the receivers for an EMG system and also for the inertial motion capture system. And they transported like various kinds of merchandise from this little transport cage. And we took 12 common, or we selected 12 common handling tasks were included, and that could be the handling of boxes of bananas, boxes of milk crates, cucumbers, and a lot of other merchandise. So, and also it was able to all these different merchandise could be handled from different positions and to different shelf heights. So we had multiple start and end positions included. In the end, we had 50 lifting conditions in total, and we performed 4 repetitions per condition. So here is also just an illustration of the inertial motion capture and the surface EMG data we obtained during the stocking work. And on the left-hand side, you see the setup where we do the subject or the system calibration for the Xsens window system. And on the right-hand side, you see one subject performing handling of boxes of bananas. And also, if you can see on the bottom right-hand side, is just an illustration of course, we use this the framework that Powell just presented, which takes us from the kinematic model in Xsens, and use this concept of virtual markers to actually drive and make the kinematic analysis in AnyBody, and as well as the kinetic analysis. So from all this data, this is just some of the data we actually used in the publications and in the database. But we extracted the peak trunk, knee, and shoulder flexion joint angles directly from the Xsens software. And we also extracted the peak L5S1 joint reaction forces, as well as the knee and shoulder resultant joint reaction forces from the musculoskeletal models. And then we used repeated measures linear mixed models to estimate least square means of the peak forces and peak joint angles with 95% confidence intervals. And this was used to rank all the manual material handling tasks according to all these outcome variables. So for example, the spinal loads, and you rank all the tasks from the highest load to the lowest load. And this is what you're going to see if you go into the database, for example. Then you have these rankings for all the tasks. So if we first look at some of the postures estimated with Xsens, we found that 14 of the 50 tasks we analyzed involved lifting to above shoulder height, which of course is quite a well-known risk factor for developing shoulder disorders. We also found that 22 of the 50 tasks involved like a high degree of trunk flexion, so trunk flexion above 50 degrees. And we also found that 20 out of the 50 tasks involved knee flexion above 70 degrees. So meaning that they had to squat down quite excessively to pick up or place the merchandise during the handling operations. So if we look at some of the models, of course, there are many more like this. So this example is the handling of milk crates from a low to a low position. So being approximately 15 centimeters above the ground plane. And if you look first here on the left, you have the actual compression force in the spine, as well as the anterior posterior shear force. And you can see there's these two peaks, one at pickup and one at deposit. And you see the whole lifting cycle here from 0 to 100%. As well, you also see the knee joint reaction forces, which has a much higher variation. And if you notice on the video, you can see that they actually have to squat down and turn and walk with the load. And of course, not every person does this the same way. So that is also why you see a higher variation in these forces. But you particularly see a peak here, for example, in the left leg, and where they squat down quite a lot, or flex the knee quite a lot. And also during deposits where they're standing mostly on one leg for support. If we go further and look at the handling of breadth, this is from a high to a high position. So higher starting position, approximately 75 centimeters above the ground, to the highest shelf height. So you can see actually a shelf height that's above shoulder height. So here you see a somewhat lower compression and anterior posterior shear force in the spine. And of course, since they don't have to what's called it, flex the trunk to pick up the load, you see a quite consistent load here in the compression and shear force in the spine. What you also see is the shoulder joint reaction forces, which increase quite dramatically from picking up the load and actually placing it on the shelf above shoulder height. So again, in the database, you'll have many more outcome variables and many more tasks, which we did the model simulations on. So check that out if you feel like it. So one really nice thing that we could do from this type of analysis is that, of course, we could estimate the actual compression force in the spine as well as the anterior-posterior force. And we could compare these also to these quite well-known tolerance limits or injury tolerance limits. One being this 3,400 Newton tolerance limit for compression proposed by NIOS. Another one being the anterior-posterior shear tolerance limit proposed by McGill and Gallagher and Morris of 1,000 Newton. So here we just have the top 10 ranked on the left side for compression and the right side for the shear force. And you see that we actually found quite a few tasks, like 8 for compression, 6 for shear, which exceeded these well-known tolerance limits. And we chose to use the upper confidence limit because this was the more protective approach in our opinion. But you see that it's mostly all these variations of handling milk crates, which weighed approximately 17 kilos, as well as handling bananas, which weighed approximately 20 kilos. So here we can actually go in and make some quite specific advice about possibly avoiding these specific tasks. So just to sum up the main findings here, we found that based on the Xsens estimated joint angles, we found that a large proportion of the analyzed task involved undesirable working postures. We also found that spinal loads exceeded tolerance limits for both bananas, milk, as well as cucumbers. We found that load weight, start, and the end position had considerable influence on the musculoskeletal load. And we also found that lifting cucumbers and bread to high shelf resulted in the highest shoulder forces by far, about two times the subject's body weights. And we also found that the weight of the merchandise, as well as the handling technique, how much you squatted down, how you walked with the load, if you only supported yourself on one leg, for example, were the main predictors of high knee forces. So of course, this led to some practical recommendations for the industry, which I'll very quickly go through. And one thing could be that handling of bananas and milk should be reconsidered since it exceeded these well-known tolerance limits for spinal loads. One things you could do would recommend individual stocking, repackaging merchandise, or also increasing handling height, which we also found had quite a dramatic influence on the spinal loads. Also, lifting cucumbers and bread to higher shelf heights should optimally be avoided. One thing could be to remove the highest shelves, prioritizing lighter merchandise on the highest shelves. And this also goes again for avoiding unfavorable working postures. It's a good idea to get everything as close to, you can say, the center of the body as possible. So removing the lowest, highest shelves and increasing aisle space so you actually have room to move around when you have to do these handling operations. So if I go back to what also this webinar is about, is the applicability of this methodology. So based on the work I did here with colleagues as well, we feel that this methodology can provide very reasonable load estimates for multiple joints in some real-life working conditions. And I say some because we still needed to standardize the handling operations to some extent. And that was particularly for the hand placement on the merchandise is quite important because we need to accurately define this in AnyBody. And it was also just to avoid a very, very large amount of variation in between subjects and within subjects when you're doing these handling operations. There are many ways you could do this, which of course complicates the data processing, particularly in AnyBody. Also, we found that it was quite sensitive to inaccuracies in the kinematic data. Particular thing would be the hand position, where we, for some trials, saw that the actual hand position was not so accurately estimated, which meant when you had to fit or define the contact between the boxes and the hands would be too close and the box would be oriented. There was errors in the orientation and the position of the boxes. But this was mostly a trouble when they were handling very small, narrow boxes. And of course, it is quite time consuming. One thing could be the need to, for example, set the initial posture when you have to make AnyBody model track the kinematic data from Xsens. In my case, I had 3,000 trials. So of course, if you have so many trials, these little things can take a lot of time. And also we encountered some muscle wrapping issues. But I wouldn't even go so much into that because if you have the newest version of AnyBody, they implemented a new experimental muscle wrapping algorithm, which actually solved a lot of these problems that we experienced during the data processing. So luckily that won't be a problem moving forward. Some things to remember is also that other methods are also quite time consuming and difficult to apply, whether that is video recordings or if it's EMG or something else. It also takes time, and you actually won't get the same amount of information as you would using this approach, because there is an abundance of information suitable for additional analysis. And as Paul also mentioned, has one example is that we made an exoskeleton evaluation on the same data sets we collected from the supermarket. So you can actually see how, for example, one exoskeleton design would reduce the loads in the shoulders in this case during some of the more strenuous handling activities. So lastly, strengths and limitations of this study. To our knowledge, it was the first study to estimate multiple 3D dynamic joint forces during manual handling based on field measurements. And of course, you get a relatively accurate estimation of postures and the acute loading of multiple joints. So you have a quite accurate and very vast amount of data you can look into to do ergonomic evaluation. One thing we did not look at was cumulative load, so which is something you as well doing when doing ergonomic analysis is also very important to consider because we found in the supermarket sector that there is a dose-response relationship between cumulative load during multiple days and the intensity of low back pain, for example. So if you want to get the full full picture of the hazards during this handling, of course you need to consider this as well. Another thing was the limitation was that we did not accurately capture the natural intra and inter-subject variability. And this was mostly due to us having to some extent, standardize the lifting activities. At this, of course, you should try to do this as little as possible, but doing a little bit of standardization will help you a lot when you especially have to do the modeling part of the analysis. So in the conclusion, we felt that the methodology was in its current state mostly applicable for in-depth analysis of potentially hazardous tasks. So for example, instead of, as I did, measuring 50 different tasks and trying to model all of them, you could use more simple observational methods to try to pick out what task would present the most hazards and use AnyBody, for example, to take a deeper look into the loads associated with these tasks. So that was it for me, and thank you for your time, and of course check out all the material related to the publications if you are interested.
Thanks, Sebastian. I already saw some questions popping up for you as well, so very interesting presentation. Next one who's up, Jason Conrad. As mentioned before, he will go a bit more in depth about looking at the daily activities of elderly and what the effect is of the joints. There he is, Jason. Feel free to take over.
Cool, can we all hear me? So I just need to share screen. How do I do that, Felix?
You should get a pop-up now to activate.
There we go, show my screen. Okay, I've got two screens at the moment. I've got the presentation on one. Can anyone see that yet, or do I need to drag it across to this one?
We can see the PowerPoint now.
Yeah, okay, that's good. Nice and smooth. So let's run this from the top. Beautiful. So good evening, everyone. Oh, it's probably good afternoon for you guys. Down here in Australia, we're into the evening. So Good afternoon and good evening. So I'm here to present some of the work that we did in the NEMO project. So the NEMO project was a fantastic research collaboration that we had amongst multiple groups. For this particular study, this was back when I was involved with Xsens, and I had a secondment at Aalborg University. So I actually went over to Denmark and spent some time in the lab there with the guys from AnyBody and with the guys at Aalborg University. Fantastic group there. I just wanted to give a sort of, I guess, a shout out as well to the co-authors involved in this paper, Angelos Karatsidis, Martin Scheppers, Giovanni Belushi, Mark Dezea, and Michael Skipper-Anderson. Great bunch of people. And so what we were looking at in this particular study was essentially estimating knee loads just using kinematic approaches. So this is actually also published in the Journal of Sensors. So the title of that is Estimation of the Knee Adduction Moment and Joint Contact Force During Daily Living Activities Using Inertial Motion Capture. So just to give you some background in that, knee osteoarthritis is a major cause of pain and disability in the elderly population, as well as many others. It affects millions worldwide. You also find people that have undergone ACL injuries and undergone ACL reconstruction. Around 50% of them also develop osteoarthritis within 10 years of the reconstruction. For this particular study, we were looking at the elderly, so people above the ages of 50. So when you actually look at knee osteoarthritis, it typically affects the medial compartment of the knee, and you'll find that you'll get that degradation of the articular cartilage. But you'll also see the presence of bone marrow lesions in that subchondral bone, and that gets worse and worse with the severity of the disease. And typically the end stage result or the terminal result of that is knee replacement surgery, which is never good. So what we know is that the cartilage of the knee responds to the loads applied to it. So characterizing this mechanical loading can provide valuable insights into the development of OA. So as part of this NEMO project, we had many work packages. People were looking at imaging studies, musculoskeletal models, but we're also starting to look at different technologies which we could use to start to look at load. So we're also looking at, in terms of daily monitoring as well. For example, there was work done with pedometers, but we're also looking at alternative technologies to start to investigate this. So using inertial sensors naturally came up with this, and I'll go into that in a second. Typically, when we discuss loading, we need to actually understand what loads are happening in the joint. What can happen is we can also do, for instance, inverse dynamics to look at the torques going through a joint. Now, that's not actually representative of the actual joint contact force when we're talking moments, but in the past and throughout the literature, you'll see that the knee adduction moment has been a convenient surrogate to estimate the medial compartment loading, because the knee adduction moment essentially puts that bending force and we load that medial compartment of the knee joint. But if we also look at the tibiofemoral joint contact force using a musculoskeletal modeling approach, in which muscle forces can also contribute to that, that can provide valuable insights. So as I said, if we can characterize the mechanical loading, we can provide valuable insights into knee osteoarthritis. So when we actually start to look at daily living activities, particularly in the elderly, we can see that they start to struggle with some of these. So if we look at stair climbing, that's actually one of the most difficult tasks for people that suffer from knee osteoarthritis. It places greater demands on the range of motion of the lower limb than walking, and you'll find, especially walking downstairs, we can really load that joint, and especially we also load the muscles eccentrically just as we lower, for instance. And you'll find a lot of patients with knee osteoarthritis, they can adopt compensatory movements. They can lean the trunk forward, and what that can typically do is reduce that knee extensor mechanism. So even just inertial sensors in themselves, before you're actually going into musculoskeletal modeling approaches, can provide insights, because we can actually start to see compensation movements aside from healthy gait patterns. So you'll also find, for instance, getting in and out of a car, it can really load that knee joint as well. So thus, we wanted to also start to look at that sitting to standing movements, as that can be difficult for knee osteoarthritis sufferers. So prior to essentially do this, we need motion capture techniques. And when we look at musculoskeletal modeling approaches and motion capture approaches, the gold standard is typically considered to be optical motion capture and also using force plate data. So what we can do is we can actually calculate the knee adduction moment and contact force conventionally using the optical motion capture and force plates. The limitations with that is having the availability of laboratories, the cost of those, restricted measurement space. You can get occlusion of markers, for instance, lengthy processing times, and probably one of the, I guess, the biggest weaknesses of that is that we say it doesn't have that ecological validity. It's not the patient in their natural environment, and many applications can occur where it can be difficult to replicate that in the laboratory rather than being in their actual environment. So methods that we're starting to now look into, especially with inertial measurement units, can address some of these shortcomings. But prior to doing that, we actually wanted to do some validation to essentially see if what we're doing was okay. So what that brought about this initial study was a validity study comparing what we do using IMUs, exclusively kinematic data, to try and estimate these loads, and how that compares to our gold standard approaches of using optical motion capture with force plates. So the aim of this study was to use a musculoskeletal modeling approach to estimate the knee adduction moment and joint contact force during daily living activities in the elderly, using only inertial motion capture derived kinematics. So our hypothesis would be that it would provide estimates which would be comparable to those optical methods with force plates. With this, can enable applications that provide suitable estimates of tibiofemoral joint loading during daily living activities of the elderly in their actual natural environment. So without further ado, we actually we needed a method to measure stair forces, and to date, this is one of my favorite experiments to have done because it was very difficult to get everything set up. So we had a custom built staircase. So if you actually see, we initially had to have the force plates properly in the floor. So we actually had to rip out parts of the floorboards. So we had some wooden planks and we'd put them in, stacking them like a game of Tetris. And interestingly, so we've had 2 steps where you're measuring that attached independently to 2 force plates. But what you have to do is make sure that they're isolated from each other and from the rest of the staircase. So essentially, as you can see here, we've built the first and second step attached to those 2 force plates, and then we've built the rest of the staircase around that. So ensuring that nothing touches each other so that they're all isolated from one another. So the first step is registering forces from the first force plate and the second from the second force plate. So that's how we were actually able to measure the stair forces. So looking at our data acquisition process, so we brought in 10 healthy elderly patients. They were recruited from the ages of 50 to 75, and we brought them into the Human Performance Laboratory at Aalborg University. For the inertial motion capture, we placed 17 IMUs sampling at 60 Hertz using the Xsens window system. Just a brief rundown, we used 17 placed essentially on each segment of the body. Following a sensor to segment calibration, we can track motion. I'll go through that particular part in a second. As part of the validation, we used 8 Qualisys cameras sampling at 240 Hertz, and we placed 53 reflective markers placed on anatomical landmarks around the body, as we do in those methods. And we used AMTI force plates measuring the ground reaction forces at 1000 Hertz. So we did that synchronously, and we collected trials of stair ascent, descent, and sit to stand. And we synchronously measured those using both mocap methods. So if we look at the optical data, what we would do to deal with that first, we would use the generic AnyBody model, and we would scale that and register to a static pose. So initially, once you had put the reflective markers on and instrumented them, you would hold a static pose. And we use that static pose to actually scale that model. Then from that, we do a process called inverse kinematics. And what inverse kinematics does is it shows the marker trajectories, and it uses those marker trajectories to essentially move the model by least distance between the experimentally measured marker and the model marker. So that allows us to fit the motion to the model. Once we have that motion and working with the force plates, we can use a process, as we know, called inverse dynamics. And using that, we obviously have the most distal segment, measuring that from the force plate. Then using the motion, we can essentially work our way up the chain and calculate the loads at each joint. So we used inverse dynamics to establish the kinetics. From the inertial perspective, we had a virtual marker model, which we created using the IMU sensors. Pavel touched on that before as well. So what we essentially do is the Xsens system has 72 degrees of freedom. We then have to bring that to the 44 degrees of freedom to counteract, I guess, physiological motion. So we actually have constrained motion at joints. So this virtual marker model essentially then drives the motion of that model to inform the kinematics. So once we do that, we would perform inverse dynamics, and that's using the ground reaction force prediction algorithm. Probably Sebastian can tell you a lot more about that. He's used this algorithm as well. Essentially, what we would do is we would detect steps from height and velocity thresholds of the foot sensor, and the model actually has nodes in the foot, and from that it works with known friction coefficients, and we can then estimate the magnitude of the ground reaction force and the center of pressure, and with that we can run inverse dynamics. If we start to look at the results, if we just first look at the kinematics, here I'll just show for the stair ascent. So we look at particular degrees of freedom, that being the hip flexion, extension, hip rotation, hip abduction, ankle, the ankle angle, subtalar ankle angle. That was a difficult one to say, and the knee angle. So if we look at the following figures, we'll see very, very tight curves there. And in fact, if we look across all tasks, we'd have excellent Pearson correlation coefficients with root mean squared errors between 4 degrees and 7 degrees along the sagittal plane. And across all tasks, strong Pearson correlation coefficients with root mean squared errors between 2 degrees and 8 degrees for subtalar eversion, hip abduction, and hip rotation. I believe the subtalar eversion had the slightly higher root mean squared error. And then when we come to the kinetics, so we present this, I'll present it for each one. So we have the stair ascent, and what we did, so if we have the optical in blue and the inertial in red, and what we've also done is we've done point-by-point p-value analysis to see where there would be any significant changes. But what we'd find, and if we look at things collectively, we had very strong Pearson correlation coefficients showing a good match in the shape of the curves with relatively low root mean squared errors, and the values are presented there for the knee adduction moment and the tibial joint force. Again, this is all published in Journal of Sensors if you want to take a closer look at that. And if we look at stair descent, these had the highest loads, which makes sense because it's when you're stepping down and it's when you're actually loading the joint. Strong Pearson correlation coefficients between 0.74 and 0.85, and again, relatively small root mean squared errors. And for the sits to stand, which had the best results of the 3 movements, excellent Pearson correlation coefficients between 0.92 and 0.98, with root mean squared errors presented there also. So collectively, if we look at all this, this was the first study to actually estimate these joint moments and forces during stair climbing using only inertial measurement units. We found approximately 2 body weights during sit to stand, which had the lowest contact forces of all of the tasks, and approximately 4 body weights, which were measured during the stair descent, which had the highest contact forces out of the task estimated. And as I said, that's when we're stepping down and loading the joint. And if we actually look at the values that have been reported in vivo studies, we actually see similar values reported using instrumented implants. And there's some further supporting literature of that listed there. So in conclusion, we'll find a musculoskeletal model driven by inertial motion capture provides estimates of the knee adduction moment and joint force with comparable accuracy to the same model that's driven by optical and force plate measurements. So with this, we believe this knowledge now enables applications to investigate the daily living activities of the elderly in their natural environment. Beautiful. And again, I'd like to just take acknowledgement for all the people involved in the NEMO project, the people at Aalborg University, the people at Xsens, and the people at AnyBody Technology. If I've missed anyone, I apologise, but it's been great working with you.
Thanks, Jason. Since you were the last one presenting, and thank you for spending your first day evening like this.
That's okay.
I think it's time for the Q&A session. So let
Sure.
me get everyone's webcam up and running now. If Pavo and Marcus are joining as well. All right, so let's go to the questions. And I know we had a few. The first one is for Pavel. So let me get it here. A question from Hannah. Do you use any devices to record and analyze EMG data? Let me unmute you.
Oh,
Yeah,
super.
sorry.
Thank you. Yeah, so we compute muscle activity as in a simulation. So we do not need to measure EMG measurements. This is we do not exactly predict EMG, but we compute something that has a similar nature to EMG. And because this is an inverse dynamics, we go from motion to forces. We actually use a muscle recruitment optimization algorithm to do so. So EMG is helpful, but it has also limitations in terms of how deep you can measure EMG signal and so on. So we basically compute everything, but the EMG can be used more like a validation measurement rather than.
All right, thanks. Not a question, but a remark from Damien. He really liked the bow that you added at the end, so that's good. Let's see, a question for Sebastian from Pasaya Purin. Sorry if I mispronounce. But when you do the experiment, how do you know when the lifting cycle is 0% and when it's 100%?
Yeah, so we also video recorded all the movements, and I think that also it presents one of the bigger challenges while doing analysis of handling activities is when exactly do the subjects pick up the load and when do they release it again, and where on the merchandise in this case that they're handling, where are they holding it. So we went through a kind of tedious process of looking at video recordings and using that to kind of cut up the trials. So we analyzed it from that moment they lifted up the box as when to the moment that they released it, or the instant they released it. Yeah. So if you could automate that in some way, that would be great. But it is a kind of a time-consuming task in this study for sure.
Right. I have a question from Johan to Jason, who I think is a fan of Jason. He says, "Thanks, brilliant as always. We know that depending on the surgical technique of ACL, the tensions of the graft will limit certain movements. Can you achieve sufficient precision with the use of Xsens alone to obtain the rotation of the knee, so the tibial plateau in relation to the femur?"
Yeah, it depends if you're also wanting to look at translation. Not sure with respect to the translation. I know with respect to the rotations, it should be okay within certain degrees of error. I know definitely along most degrees of freedom, you're looking at within 5 degrees. But that is indeed correct, especially when you look at especially the tightness of the graft can really influence those subtle movements of the internal joint kinematics. Some of that might be more difficult, really, especially if you're looking at if you're really looking at fine kinematics within internal joint kinematics. The best methods for that is actually using image-derived methods, especially if you're looking at perhaps post-surgery. If you really want to know, especially how the actual cartilage itself might be loaded and potentially estimating strains in the ACL itself, probably position measurements would be better for that because it's better for actually measuring that translation. And indeed, when you get that altered internal motion within the joint, you can get regions of cartilage that were used to being loaded before that aren't being loaded as much, and regions that weren't being loaded as much before sort of being loaded more. So those subtle joint motions, probably better actually using image-derived methods where you can actually, for instance, take an MRI, fit spheres or cylinders, and then actually seeing how they move with respect to one another. So if you're looking at very high fidelity models, in post-surgery orthopedics, probably image-derived joint kinematics may be better. But as I said, there are many more simplified questions that you can answer, for instance, just with the inertial method. So if it's more simple joint rotations, that would be okay. But if you're starting to look at perhaps anterior tibial translation and things like that, how that's changed, especially if you're perhaps doing finite element models of the cartilage or models to actually estimate the ACL strain. As I said, probably using those MR methods would be better. But for simple joint rotations, yeah, within the degrees of accuracy that we have with the system, we will have, of course, smaller errors compared to optical motion capture. But like I said, I think they're quite good, sort of within that 5 degrees.
Yeah. And second question for you, what is the degree of freedom of the knee joint for both studies? So does 2 or 3 degrees of freedom have any difference on the knee results?
Possibly. We just had 1 degree of freedom. That's an interesting question, because if I look at the models that I used in my PhD looking at ACL injuries, we had 2 degrees of freedom, whereas flexion extension also had internal external rotation, and we locked it in the varus and valgus. Whereas the AnyBody model is just at 1 degree of freedom. And Pavel can probably comment further on that.
Yeah, I actually wanted to comment is that yeah, I think by default we of course have 1 degree of freedom knee model, but we also have sophisticated definitions of the joint motion. So we have some that float and have a little bit of elements of internal external rotation. There are also options to have like a surface-based definition of the contact, and maybe it could be a way to approach. If there is interest, I think we have a webinar with Michael Skipper Anderson as well, who won a Grand Challenge competition in predicting knee forces, and this used a hybrid solution where basically the only important part of the motion was the knee flexion angle, which can be achieved with Xsens data. So maybe it's the way to go, but of course it's a little bit special analysis.
Yeah. All right, thanks. A question for Sebastian. Thank you for the interesting presentation. Did you encounter any issues with the IMU orientation accuracy, such as an offset in the IMU heading, drift, or similar issues when you performed measurements in supermarket environments, where you might have disturbances that are not present in an ideal motion lab, such as ferromagnetic shelves and refrigerators?
Yeah, of course, this was a problem that we were quite well aware of, and of course, Xsens has gone through a lot of trouble to try to minimize the effects of these magnetic distortions. So, like, we didn't see any like major issues, I would say, with magnetic distortions. But it's of course it's not something that we specifically evaluated. We evaluated visually, like looking at the models, looking at the video recordings, doing frequent calibrations. So every time we moved to a new area of the shop, or if a certain amount of time had went by, we did a recalibration, for example. Because the mostly it was actually the position, you can say, of the model. If you, for example, walked around a lot in the shop and you would go back to the same spot, yeah, the model would have moved to some degree, and that would actually be the only issue that we saw. Not something that particularly affected our analysis in this case. But of course, it is kind of a little bit of a black box. It's we don't really know for sure how much these like magnetic distortions affected the data. But from my experience, it wasn't a big problem. No.
Yeah, so maybe to comment on that as well. So since the new software engine that we released in 2018, we worked quite a lot on developing algorithms for magnetic immunity. And you can find quite some validation papers on our website. If you go to Xsens and then go to research and validation papers, you will find them. So yeah, typically you won't have any drift when you are in magnetic environments. Like Sebastian says, it works a bit like a black box, because obviously the algorithms that are being used are IP. So the only thing that we can do is show with validation papers, and preferably external validation papers, that the result is accurate. And I think that's the thing that matters in the end. So a question for, let's see the next one. A question for Marcus. Let me unmute you as well. So the question is, can you use Xsens to allow input in Unity, Unreal, for example, also for VR experiences? So can you get like a 3D live stream into those programs?
Yeah, so you can. We just a general comment for Xsens users that we have a really nice knowledge base on our website. So if you go Xsens, www.xsens.com, and then on the right top side, you can find resources where you can find the knowledge base. And if you search it in the search box Unity, you can actually find an article which goes through the step-by-step instructions on how to set it up.
Thanks, Marcus. Maybe also good to add here is you can go to tutorials.xsens.com to look at some video tutorials as well, also for setting up these kind of streams. A question for Jason. Would you say that the RMSE that you observed between the IMC and OMC are neglectable, or do they have any clinical relevance?
Oh, most definitely. I think you find there'll be some regions where there was gaps, but I think in the more important regions where, for instance, you're recording the peak force, the RMSEs were sort of lower. So typically, it's typically when you're looking at those peak events that they matter quite a lot, and they're sort of reduced there. That's exactly why we did and it was on the request of the reviewers as well when we went through the publication process, was actually showing the point-by-point p-value analysis to see whereabouts during the cycle more errors were occurring than others. So indeed, it can be used with great clinical relevance, because as I said, what we do and what's happened with the literature and with respect to the near adduction moment, we've found it's a very convenient surrogate, and we find that if you actually look at it over the progression of the disease, it can be very useful for that, for looking with the progression of the disease. So indeed.
All right, the next one, question to Pavel. What are the main challenges that we face when estimating forces from the hands? Can we use the same nodes as on the feet? Are there any equipment available, for example, gloves, or how does it work?
Yeah, that's a good question. Of course, the human hand is a little more detailed, and I think there are different products on the market that can measure forces on the hands, and I believe Xsens might have some related products. Maybe it's they can also answer this question. But yeah, so I'm aware of some products that can measure kinematics of the hand and kinetics. And yeah, the challenge is to get the data. I think there are also some very detailed hand models that can be used to do some like hand analysis. But I think the major challenge is to obtain the data, of course, and it has to be accurate enough.
All right. I think looking at the time, it's time to maybe do one or two more questions. We have quite some questions left as well, but as mentioned before, we will make sure that they get delivered to the right presenter. As well as if you have any questions afterwards, feel free to shoot them to info@xsens.com so we can also forward them to the right person. So question to Sebastian. Did you always set up the Xsens avatar sizes according to the test participant? You said 3,000. Do you think it is possible to predict forces statistically speaking from different sizes of people than the one on the mocap?
Oh, that's a good question. Like first to the first part of the question, yeah, we had 3,000 trials in total, so that was like the 50 lips, 4 repetitions, and 17 subjects. But of course, the models we used were based on the manual measured segment dimensions, which we did on the measurement day. which we also found in general were quite consistent. For example, when we did an evaluation with marker-based motion capture, so the scaling of the model was actually quite similar within 1 centimeter, typically in our case. So the other question was if we could kind of predict, so to relate those forces we measured on this sample statistically to other sizes of people. That was kind of, if I've understood it correctly. Yes, I guess you can do that. You could do it with anybody, I guess, like if you had different, it's a simulation software, so there you can of course change a lot of parameters in anybody if you want to check how different sizes relate to a certain task that is already defined. But of course, in our mocap examples, we only have the task and the people that we actually measured. So maybe you could, Paul, maybe you could comment on that if you have anything to add. But yeah, usually would use like quite big databases for that kind of analysis. I would say many different lifts, right? So you can divide them into some kind of percentile of the top population, for my understanding.
Yeah, I could just add that it is possible to impose joint angles of one person onto another one, but there are of course some challenges that basically we do not have the same inertial distribution of masses all over the body, so the balance of the model changes. So if you could make some corrections for that within the model, I think you can use that. So I think there are some techniques and some motions that are easier than others. So in principle, it is possible, but it requires some special considerations.
All right. So the last question from Catherine. You had questions whether the MTW trackers from Xsens can be used with AnyBody. So yeah, to briefly answer this one, the MVN Awinda exists of MTW sensors, so you can definitely use it. The minimum requirement within Xsens is that you use at least 7 of these trackers for a lower body setup. If you want to do a full body, you need 17 of these. But yes, you can use this hardware, but also the MVN link to get the data into AnyBody. As said, we still have some questions left. We will make sure to forward them to the right presenters, so you will get an answer to it, hopefully. I would like to thank you all for participating, and especially the presenters, obviously, that took the time to present this work to you all. And we will share the recording of the file afterwards, where we will add the video that didn't work together with the sound. So you can take a look at it again if you want to, or share it with colleagues for which this might be interesting. So thanks again, and hope to see you with the next webinar.